Today we are looking at an interesting topic on DNS called DNS security. DNS security is an extension of the regular DNS. It actually provides some measure of authenticity and integrity to the process of name resolution. First, what is DNS? DNS is simply domain name system. It's a scheme that actually translates the typical names you and I know for websites and URLs into address, such as IP address, such as like 142.250.188.142, and any other IP address that you can think of. The primary goal of DNSSEC is actually to provide, like I mentioned before, authenticity of the data that you receive from name servers or zone servers, and also to validate that that data has not been tampered with, which is the integrity check. It all starts with a client making a request. A client is a typical web browser such as your Chrome, your Internet Explorer, Firefox, whatever you call it, sitting on your laptop, and you want to browse on a website. Maybe the website is www.example.com. It could even be www.cnn.com. And so that is the resource you want. You enter that resource, and then the process of name resolution starts. Your system takes it from the browser, and using what is configured on your system IP settings, one of them is actually your DNS server IP. Your system will now send that request to your DNS configured IP. And for many users, it's actually 8.8.8. And so your system sends that request to 8.8.8, which happens to be Google's public name resolver. And this query gets to the name resolver. The name resolver will now take that query and say, what is this person trying to get? This URL. Is this request a DNSSEC type of request? Now, how do you know whether it's a DNSSEC type of request? There is usually a bit of the record that is set in the information that the name server, the resolver in this case, is sending out. So if it has a DO bit set to 1, it means this query is not a regular DNS query, but a DNSSEC query. And so it goes through a recursive process of getting that requested IP. And eventually that recursion takes it to the root server before it now comes back down to the resolver, which now serves that record to the client. All DNS queries use UDP because of its speed. The only time you have a DNS query that runs on TCP is when there is a zone transfer. But for normal record queries, it is actually done on UDP. Now, for DNSSEC, you have what is called the chain of trust. In other words, this actually explains the authenticity of the process. How does it authenticate that this record is actually coming from the zone server or the root server that claims to have sent it? Now, every query begins by the resolver reaching out to the root zone server. So the DNSSEC relies on a chain of trust starting from the root zone server, which is signed with a key signing key to ensure its integrity. So the root zone server signs the record for the top level domains. So what are top level domains? .com, .org, and the likes. So these are top level domains, and you have those top-level domain are called zones. For each of them, it's a zone. .com zone, .org zone, like that, And once the root server is publishing the top-level domain's key for a particular zone, it also signs it, so that when the resolver receives it, it tries to decrypt the hash of that signature and compares what it finds with the key for that top-level domain that the root server has published. And if they are equal or the same, then it knows that that key is authentic, and the server that sent it is also the authentic server. And it continues down that line, continues down that chain from the top-level domain that also needs to publish the keys for the various zones that is under them. For instance, if the top-level domain is a .com, there are other zones that may have registered under that .com. Example.com is one. Google.com is another. CNN.com is another. So these are all sub-level domains under the top-level domain. Now, for you to be able to validate the authenticity of the sub-level domain, the top-level domain also signs the key of the sub-level domain. And that key is called a delegation signer hash, DS hash. So it now shares that DS hash along with the sub-level domain's public key and its own public key. Don't forget, signing is always done with private key, by the way. Signing is never done with public key. Signing is done with private key. So when the top-level domain signs the public key of a sub-level domain, you get a delegation signer hash, right? Now, for you to decrypt that hash, the top-level domain will also publish its own public key, not its private key. Then the resolver can now use that public key of the top-level domain to decrypt the delegation signer hash. Whatever value it finds, it compares it with the published public key of the sub-level domain. And if it is the same, it knows that it actually has an authentic information, and it's actually. So now, what is the special records in a DNSSEC query? I have mentioned some of them in the previous slide, but there are additional records that comes to play as it gets down to the final zone that is supposed to now provide the IP of the resource you wanted. Now, we have RRC, which is resource record signature. This is one encryption hash, signature hash, that is released along with the other public information for that record, for the sole purpose of getting the resolver to validate that that record that is public is actually authentic. So by the time the resolver decrypts the hash, this RC hash, the value it gets is supposed to be the IP address that was already published and sent to it. That way it can match them and validate whether it's the same or not. If the decrypted RC is not giving the same IP, it knows that the information has been tampered with or is not authentic. Now, what is used to do that decryption is called the DNS key. Again, it comes back to the same key I mentioned in the previous slide. Now, here I try to practically demonstrate this in an animated form. So you have the actors in the name resolution process here. First, you have the laptop representing the user with his browser, maybe Chrome, maybe Firefox, maybe Microsoft Edge. Then you have the DNS server, which is in this case the resolver. For many people, it's typically Google. If you are using an ISP, the ISP might actually give you their own DNS server, which is their own resolver. Now, you then have the specific resource that this client wants. In this case, it's called example, www.example.com, and this is the resolver, the authoritative zone for example.com. This is the authoritative zone for example.com. But it doesn't just fetch it straight and you see it in a minute. It goes through a chain of recursive queries in order to now finally fetch this record from example.com. So let's start. You have the client saying, get me IP of www.example.com using DNSSEC, okay? The resolver sends that request, say, get me the name server for .com using DNSSEC. Now, the resolver is sending this request to the root server. It doesn't just go to example.com. It sends it to the root server where all queries begin in the internet. So the root server receives this query, and because it says, get me this record using DNSSEC protocol, the root server responds with the record requested. Say, take the record of .com, since your request is saying example.com. So it will serve you the top level domain name server. In this case, the top level domain is .com. So take the record of the .com name server along with additional DNSSEC parameters, such as the root key and the top level domain's public key, along with delegation signer hash. It receives it, the resolver receives it and uses that information now to query the top level domain for .com. Get me name server for example.com using DNSSEC. So now it's asking for name server for example.com. Recall that in the first query sent to the root server, it didn't say example.com. It said, get me the name server for .com so that I can get my records. Now it's asking for example.com. So the top level domain name server, authoritative server, now says take record for example.com along with these other DNSSEC parameters again, like the previous one. It uses that information now to say, okay, I have the name server for example.com. It now sends a query to that name server. Get me the IP. It's not asking for name server anymore. It's now saying, because this is the authoritative server for example.com. So get me the IP for www using DNSSEC, because the resource requested for is actually www.example.com. So it's now on the authoritative name server for example.com. The only thing it needs to ask for now is the www resource. And it sends that request to the authoritative name server, and the name server responds with the IP. Say, take record for www along with r siege this time and the key. So the r siege and the key is just the DNSSEC parameters for validating the records it is serving. It uses that to do all the validation, like I explained in the previous slide. The validation starts with the record and starts checking the r siege, validates that, now uses the DS to validate the keys for the authoritative name server, for example, then validates the key for the top level domain.com, then finally validates the key for the root. If all checks out well, it now serves the IP to the client, and that concludes the cycle. The client can now use the IP to directly connect to the requested resource on the internet.